Okay, let's look at an example now. When you're reading a time value of money problem, it's very important to think about all the information given to you and to understand what exactly being asked, because that's what's going to dictate the equation you will eventually use. So when we have a question like this, you deposit $10,000 into an account earning 5%, and when you see earning 5%, this implies interest rate, some sort of growth rate, so this is going to be the I in our equations. And when nothing else is about the compounding frequency is provided to us, what we assume is this is an annual rate, right? Earning 5%, essentially it's implied that this is 5% per year, okay? How much will you have in the account by the end of year 3, all right? So when we have a question like this, so think about our different equations we have. Which one do we need to use? So we have a single cash flow situation going on here. We have a single deposit, and now we are trying to figure out how much is there going to be in the account. So we need to think about our single cash flow formulas. What are we being asked? What are we trying to find? We have $10,000 today, and we are trying to find how much is there going to be in 3 years. So we are looking for the future value, okay? So we know when we have single cash flows, the future value of a single cash flow is given by PV, present value. So future value equals to present value. Present value here is the amount that we are depositing, right? The earlier amount is the PV, the later amount is the FV, times 1 plus I, that growth rate, right? So that's going to go into that I, 1 plus I. Since this is a compounded growth, where we have this amount that's growing, we are not taking money out, right? We are keeping whatever is earning interest, we are keeping it in the account. So we have compounded growth happening. So we are going to have this exponential term, PV times 1 plus I raised to n being how many years is the PV earning that interest rate, right? So if you look at this question, then we plug the numbers in, we don't know FV. PV is $10,000 times 1 plus the interest rate. The interest rate is 5%. We always convert percentages into decimals when we are plugging them into our equations, right? So we are going to convert that into 0.05, and then we are going to have raised to n. N here is always the time where this growth rate is applied to. All right, so for how many years, for how many periods, our $10,000 will earn 5% for, it says end of year 3, we are at 0, so this is 3 full years. All right, so n is going to be 3, okay? And if you plug these in a calculator, what we will find is the answer will be $576, and then when you have a large number and many decimal places, what we're going to do generally, unless stated otherwise, is you're going to want to round it to the, when we are working with dollar figures, we're going to round them to the nearest cent, so 2 decimal places, right? So $11,576.25, okay? So approximately, okay? So that's it, right? Read the question, figure out what we are being asked, narrow it down to the right formula that gives us the future value of a single cash flow, plug the right numbers in, don't forget to convert the percentages into decimals, and round it to the nearest cent, and that's the answer. So now let's take this one step further. How much interest did we earn? Right, how much interest did we earn? Think of it this way. How much did we put in, and how much did we take out? We put in $10,000, and we have $11,576 and some change at the end of year 3. The difference is going to be the interest we earned, right? So in a single cash flow problem where you have only one deposit, and then you have the total amount savings in the account, when we are thinking about the total interest, total money in the account minus how much you put in. In this type of simple problems, single cash flow problems, the total interest will be given by FV, how much we have in the account at the end, minus PV. All right, so that will give us the total interest. So 11,576 minus 10,000. So we have roughly, we've earned 1,576.25. That's the total interest we earned on our initial deposit of $10,000 in the account. Now this is an interesting point. Let's think a little bit more about this. And let's see the magic of compounding here, right? So what if we had earned simple interest instead of compound interest? Now what does that mean? That means instead of letting our money grow in this account uninterrupted for 3 years, what if we only kept 10,000 in the account at a time, meaning that after 1 year of earning 5%, we took the interest out and just left 10,000. So 10,000 earned another 5% in year 2. And then at the end of year 2, we took that interest again, the interest earned, and left only 10,000. And then it earned another 5% interest. So this would be a series of simple interest earned over 3 years, instead of letting everything grow. If we had done that, we would have only earned 5% of 10,000 each year, right? So 5% of 10,000 is divide by 100, multiply by 5, or also divide by 20. It's $500 a year, right? 10,000 times 0.05 is going to be $500 a year. So every year, 500, take it out. Year 2, another 500, take it out. Year 3, another 500, take it out. So in addition to our initial deposit of 10,000, we will have earned 3 times 500, so 1,500 in interest. Now look at what we earned here by not taking the 500s out, by compounding our money. Instead of 1,500, we earned 1,576.25. Now this doesn't sound very magical, perhaps. This doesn't sound like a big deal. But that's because here we are working with a small n. Magic of compounding really kicks in when you have very large n. So if we had left our money for 20 years, compounding would have really made a huge difference, or 30 years or 50 years, right? And you can do this on your own as an exercise. Do this with 5% and with a large n, and you're going to see compounding make a very, very big difference compared to the simple interest scenario. As well as the I, the interest rate. So if he had used 8%, 9%, those are not meaningful interest rate numbers anymore in the state of the world we are in. But think of it as perhaps stock returns in the stock market, earning, say, 10% for 30 years. Compounding will make a big difference, okay? One more thing I want to do while we have this question set up here is, let's change things. Well, we can actually keep this. Let's keep that. Let's erase these. Let's change the timing. Again, as I mentioned before, timing in time value of money is, of course, very, very important. So same cash flows, 10,000, 5%. How much by, let's say, by the beginning? Of, say, year 5. Right? So how much will we have in the account by the beginning of year 5? So we're going to use the same equation. Nothing fundamental has changed. We are looking for the future value of a single cash flow. Interest rate is the same. What has changed? N has changed. But we got to be careful, right? Beginning of year 5. So now what are we going to do here? We have the same 10,000 times 1 plus 0.05. Now, how many years are we going to earn 5%? Beginning of year 5, remember from the timelines, beginning of a year is the end of the previous year, same thing, right? So think of it as the end of year 4. So in that case, we have 4 full years where our 10,000 will earn 5% interest, right? So we're not going to earn interest for 5 years because we are stopping at the beginning of year 5. So we don't have that extra year. What we have is 4 full years. So our N is going to be 4. Just because of this beginning, right? End of year 5, we would have N5. Beginning of year 5, we have N4, okay? So then if we crunch the numbers, we are going to have 12,155 point, remember, round to the nearest cent, unless otherwise stated, 0.06. 12,155 $0.06, right? And how much is our total interest? So not surprisingly, we now have more compared to the previous example where N was 3. An extra year of compounded interest gave us this much savings by the end of year 4, beginning of year 5. And now our total interest is the amount at the end minus the amount we put in, $2,155.06. So future value of a single cash flow.